Today I'm going to talk about decision analysis, mostly about cost-benefit analysis, but I'll talk about its alternatives as well. And then at the end, I'm going to show an application to the London super sewer. Now, this is where we are in the series. This is week 3 already. The problem with the material of week 3 is that it should come both before and after the material of week 6, and both before and after the material of week 9. So there's going to be a little bit of circularity that is unavoidable. So I'm going to assume that you've done this already and that you've done this already in part, right? Similarly, this is going to assume that I've done this, and this is going to assume that I've done this. So it is really circular, but just suspend your disbelief for the moment. Those things will come. I noticed that you guys are not making use of the IA, what does that stand for? Intelligence, artificial intelligence, AI, TA, teaching assistant yet. It is really there for you guys. So if you haven't explored it, that maybe because everything is clear, maybe because you haven't discovered it, or maybe because you're not studying yet. But it's really there for you guys, not for my pleasure. So do make use of all the material that is there. I'm going to talk about cost-benefit analysis before we talk about its alternatives and before we kind of apply it. And I'm going to start by efficient flow pollution. But before that, just some introduction. This is by Robert Solow. Economists have the reputation of being unimaginative bean counters, doggedly claiming to quantify the unquantifiable and personifying Oscar Wilde's definition of a cynic as someone who knows the price of everything and the value of nothing. It is true that they, that is the economists, would give a lot for a rough quantitative answer, but it only reflects the fact that any policy can be pushed harder or less hard, further or less far, and that a useful evaluation has to suggest how hard and how far. The beans have to be counted, if only approximately. So far, this is cost-benefit analysis, right? This is public policy. And then, of course, Solow being Solow, he adds, those gentle souls who merely ooh and ah over them are arguably part of the problem, not part of the solution. And that's what we're going to do. We're going to count the beans, and we're going to use the counting of the beans to say how hard a policy should be pushed, right? Now, this is fairly long. Abraham Lincoln said it more succinctly. The true rule in determining to embrace or reject anything, in this case public policy, on the environment, is not whether it have any evil in it, but whether it have more of evil than of good. So we're looking at trade-offs, right? And if there's no trade-off, if something is pure evil, or if something you should reject it, or if something is pure good, then you should just wholeheartedly embrace it. But most things have a mix of advantages and disadvantages. Johan Cruyff said it even more succinctly, that every upside has its downside. And those are the trade-offs that we're going to look at, right? And we're going to start by looking at flow pollution. But first, a few words about pollution. As I've argued now a couple of times already, pollution is an externality, that is the unintended and uncompensated impact of some economic activity on a third party. In order to solve a problem, you need to have at least a rudimentary understanding of the problem as well as its solutions. And environmental pollution depends on things that happen in the environment, which can be quite complicated. The chemistry, the physics, the biology can be quite complicated. And that is known as transport and transformation and assimilation. And if you take the example of acid rain or acidification, then an important source of acidification is the sulfur that is contained in coal. As long as the sulfur is in the coal, it is harmless, right? It sort of reduces the thermal efficiency of burning of the coal, but other than that, it doesn't do much harm. When it is combusted together with the coal, it becomes sulfur dioxide. And sulfur dioxide is not at all bad for you or for anything for that matter. In the atmosphere, when it reacts with with oxygen that is around there, it turns into sulfur trioxide, which is still completely harmless. And it's only when it gets into contact with water that it turns into sulfuric acid, and sulfuric acid is harmful, right? And you need to understand what is actually doing the harm, where does it come from. Through this long transformation process, the sulfur actually travels, and it travels, I mean, some environmental problems are extremely local. So if you have a waste incinerator and the temperature of the waste incinerator isn't high enough, then you create dioxins. And dioxins are extremely carcinogenic. Good thing about dioxins is that they rarely travel further than a few hundred meters. So you have very localized pollution, also very persistent pollution, right? I mean, the dioxins that were dumped onto a field decades ago are still active and still harmful, but they don't travel very far. Sulfur dioxide or sulfur trioxide is different in that it can travel hundreds of kilometers, not hundreds of meters, hundreds of kilometers, up to thousands of kilometers. And sometimes it makes it all the way from China to the United States, or all the way from Europe to China, because that is where the prevalent winds go. So there, even though the source is very local, it's a coal-fired power plant, the consequences are continental, right? And that is important to understand, that cause and consequence can be separated, in this case in space, because the travel time takes about 2 weeks, right, is the max. Other things stay around much longer. So it is important to understand where does it come from, where does it go, where does it cause problems, and what is causing the problem. Obviously, a little bit of acid doesn't hurt a lot. If there is a lot of acid deposition, you get a lot of damage. But if you have an environment that is already so saturated with acid that everything is basically dead, then adding additional acid to the problem actually causes very little harm, because there's nothing left that can be harmed, right? So that is also important to understand, that depending on the background concentration, or as it says here, on the existing loads, pollution can be not that harmful, very harmful, or again, not at all harmful, right? And that is important to understand. Another thing, and I'll be going about this for a long time, is the distinction between flow pollutants and stock pollutants. And the canonical example of a flow pollutant is noise. That is, if your neighbor gets up at 5 in the morning and leaves his house, starts his car, that wakes you up. And presumably you will be annoyed by that. But as soon as he left the street, the noise is gone, right? So that is a flow pollutant. As soon as the activity ceases or disappears over the horizon, the pollutant, the pollution is gone. So that is flow pollution. Stock pollution is the opposite, as you may have guessed. The canonical example here is nuclear waste. That is the stuff that comes out of the generation of electricity by nuclear power. Nuclear waste, depending on what isotope you're talking about, some of them stick around, have a half-life of tens of thousands of years. That is, the nuclear power that is generated in 2025 will still be harmful to humans and other animals in the year what is it, 2025 plus 10,000, that's a long way into the future, right? And actually that's the half-life, right? Only half of the material will be gone in 10,000 years. 3/4 will be gone in 20,000 years, and so on and so forth, right? So that is a canonical example of a stock pollutant. Even if we stop using nuclear power today, and that's not going to happen, we're actually growing the nuclear power sector again. Even if we were to stop nuclear power today, the waste problem will be with us for 50,000 years, right? So that is important to consider. Aidan?
Are you for or against nuclear power?
Am I for or against nuclear power? I am an economist. Is that the answer that you were looking for? Nuclear power, I have nothing against it. The current generation of nuclear power plants are inherently safe. So the stuff that we had with 3 Mile Island and Chernobyl and everything, those problems are problems of the past. So you don't need to worry about that. The waste problem with nuclear power has in principle been solved. We have technical solutions to safely store the waste. The problem is that politicians don't want to do this. So most nuclear waste, if not all nuclear waste, is stored unsafely at the moment, even though we do know technically how to do it. So that is a problem, but it's a political problem, not a technical problem. The main issue, there's 2 main issues with nuclear power. One is that it's very expensive, not so much because nuclear power is expensive, but because of all the safety measures around it. It makes nuclear power very expensive, much more expensive than wind or solar. The second problem with nuclear power is that if you have the technology to make electricity in this way, you also have the knowledge and the materials to make dirty weapons at the very least, or nuclear bombs at the very least. Or at the extreme. And in a world that is a bit volatile at the moment, geopolitically, I am not convinced that it's a good idea to expand nuclear power to unsafe regimes, right? Where the issue is, of course, at what point, what is a safe country to have nuclear power? And at the moment, I'm not sure that the nuclear arsenal is in good hands in the United States, right? So anyway, that was not on the agenda, but happy to take questions. So I talked about flow pollution, stock pollution. Of course, most pollutants are somewhere in between, but that just makes the analysis boring, right? That's in between the 2 cases I'm going to show. So let's look at efficient flow pollution. So we're going to assume that the damages of pollution are given by a function d, and then those are a function of emissions m. And that the benefits of the polluting activity are given by a function b, and that's also a function of the pollution m. Now the net benefits are then the benefits minus the costs, no surprise there. And what we then want to do is maximize the net benefits. So to maximize net benefits, this is an unconstrained optimization problem. So we simply set d and b, dm. So this is what we want to maximize. This is what we control. We set it equal to 0. This is a linear combination, right? So dnb, dm is db, dm minus d, dm. We bring 1 to the other side of the equation, and we have an equimarginal principle that the benefits at the margin of creating the pollution should equal the damages done by that pollution. Now, for those of you who are not entirely comfortable with calculus, you can also do this graphically. So what we have here on the vertical axis is the benefits of doing something, and then on the horizontal axis we have the emissions. And then the benefits are given by a function that looks something like this. Note that we have to assume that the polluting activity creates some sort of benefit. because otherwise we would not do it, right? So going back to the example of acidification, none of you is particularly interested in emitting sulfur into the atmosphere, because why would you? But you are interested in having light, and perhaps you cook on electric power, and definitely your laptop and your phone run on electricity. So you are interested in the electricity. You're not interested in the sulfur that comes out or in the coal that goes in, but you are interested in the electricity. So these are the private gains from using, in this case, electricity, right? And at a certain point you say, well, I'm not going to use more electricity because every light in the house is on, all my gadgets are fully loaded, so why would I use more electricity, right? At one point you're saturated, your demand for electricity is saturated, and actually electricity does cost money, so if you go beyond that point, actually your net gains start to fall, and this is where you would stop using more electricity, right? That is how to read this graph. This point is then your optimal use of this particular service. You want to find the maximum. It needs to be where the slope of the curve is flat, which is the same as where your marginal private gains equal 0, right? So this is just the slope of this curve for the first partial derivative. So these are the private gains from the emissions. Now, as I said, acidification harms the environment. It kills trees, it damages sandstone and therefore most of the monuments that we have. It hurts fish, it also hurts human health. So we have also social losses from these emissions. Note that I assume that we can put these together on a graph, and that the vertical axis controls or contains both the private gains, which is your utility derived from using electricity, and the social losses, which is trees dying and monuments being damaged. And I assume that they're so commensurate that we can put them on the same vertical axis. And that will be the topic of next week and the 2 weeks after, right? How to do that. At the moment, we're just going to assume this can be put on the same vertical axis. So these are the total social losses. We then can create the net gains. So these are the private gains, the social losses. So we also have a curve, the net gains, which is simply this one minus this one, or rather this one plus this one because it's negative, right? And then the red curve emerges, and this is the social net benefit curve. And the question is, where does this, is this optimal? Again, that is where it goes flat, right? So that is one way of looking at this. Where does this curve go flat? So this is the marginal net social gains. The marginal net social gains is the sum of the marginal private gains, the brown line, and the marginal social losses from emissions. And I flipped the sign there, so the red curve goes to 0, that is where the social optimum is found, at the same point where the marginal social losses equal the marginal private gains from these emissions, right? And this point here is the optimal level of pollution. Now we have derived this, right? So this is the unregulated activity. If we ignore the social costs of what we're doing, this is what we would do. If we include the social cost, if we internalize the externality, then we will go from Q prime to Q star. That is the optimal level of emissions. Right? Now I've marked 4 areas here, A, B, C, and D. And they can be interpreted. Area B, the area under the marginal social loss curve, is the optimal level of environmental damage, right? This area here, that's C plus D, is the area of environmental damage, is the total environmental damage that would occur, the excessive environmental damage that would occur in an unregulated market, right? The total environmental damage would be B plus C plus D, but the area C plus D is excessive environmental pollution. Now, why do I say that there is optimal environmental pollution? Because there's also the private benefits of the polluting activity. And in the optimum, that is the area under the brown curve, that is A plus B, right? That is the optimal level of private gains from the polluting activity. And what you can see, obviously, is that A plus B is greater than B, right? And that justifies why the pollution is here and not here, right? These are the social costs, these are the private benefits, and the net welfare gain is A. The area that you see here, area C, is the amount of private benefit that comes at the expense of the environment, right? This is the unwarranted, the unjustified private benefit that you would gain in an unregulated market. Right? And what you can see is that obviously that this area here is smaller than this area here, right? And D plus C is greater than C. So if you're here, then indeed the environmental damages are so large relative to the private gains that you don't want to be in Q prime, right? And Q prime is a net loss to society, and we want to push emissions down. And that leads us to conclude that Q star is the optimal level of pollution. And the first basic insight here is, this picture is a year old, is that optimal pollution is greater than 0. If you want to upset an environmentalist, say this in the pub, right? And they will start screaming at you, like Kelsey is doing here. But it follows from the fact that the polluting activity brings benefits, right? Yes, we can drive the emissions of sulfur to 0 by not using electricity anymore, but then the beamer goes off and the lights go out, right? And your phone will stop working in the next few hours, right? But actually the masts will come down before your phone runs out of battery. So there are benefits of using electricity, and they to a degree outweigh the costs of the pollution that comes from generating electricity, right? So optimal pollution is greater than 0. If you want to rile up somebody, say that, right? And this follows from the laws of thermodynamics that 0 pollution implies that you can't do anything. Now, some people say, but there is such a thing as a simulative capacity. A certain amount of pollutions we can put into the atmosphere that don't do any harm. And would we not want to reduce pollution to the point of the maximum assimilative capacity? Well, the answer is no. We go back to the cost-benefit diagram. We want to equate the marginal social losses from the emissions to the marginal private gains from the emitting activity. That's the dark green line versus the brown line, and this is where we want to be. Now, assimilative capacity essentially says that the first bit of emissions doesn't do any harm. So the marginal social losses curve, the marginal social loss curve, doesn't go through the origin. Actually, the first bit of pollution doesn't do any harm, so this curve starts here, right? And assuming that the slope stays the same, it actually shifts down. And what we have is that the optimal pollution without assimilation is here, the optimal pollution with simulation is here, and we actually move to the right. We did not move to this point, we actually moved to the right, right? So optimal pollution is greater than 0. It's also greater than assimilative capacity. If you have pollution that is greater than the optimal pollution, that is because people don't take into account the impact of their activity on others. That is, it's an externality. Right? So, that is for a flow pollutant, which is straightforward. Let's look at a stock pollutant. So the benefits of the polluting activity we assume are still the same. They depend on emissions M. But the damages of pollution now depend not on the emissions, but on the stock of pollutants. I don't know why this is an A, but that's what I called it here. And the stock of pollutants, let's assume that this is a linear first difference equation. First order difference equation where the stock of pollutant is equal to the pollution in the previous period times some environmental degradation factor, 1 minus delta. So there's 100 tons now in the atmosphere. A year later, because of degradation, only 90 tons remain. Right? That is essentially how to read it if your delta is 0.1. But we're also adding to the stuff that is in the atmosphere. Let's assume that we're talking about the atmosphere and the A makes sense. We're also adding to that, right? So this is a difference equation. The stock depends on what happened in the previous period. Some sort of degradation going on, but there's also new additions to the stock every year, right? So, what we now have is the current benefits, or the net current benefits, which is still the benefits of the polluting activity minus the damages, but they're no longer a function of M, they're a function of A. It becomes a dynamic problem. So instead of maximizing this, we want to maximize the net present value of this, right? So the two innovations here compared to the previous slide, the A has become an M, or the M has become an A, sorry, and we add NPV in front of it, front of the net benefits, right? It's now the present value of this thing. Let's assume we solve this in discrete time. So the net present value is defined for all periods t. The benefit of the polluting activity minus the damages at a particular time t. Of course, discounted to today at 1 plus rho to the power t. Right? So this is again what we had before, but now we have a summation over all times. But still we can split this, right, and bring it to the other side of the equation. So really what we want to do, we want to, again, we're deciding over M, so we take the first partial derivative of the net benefit, which is the first partial derivative of this thing minus the first partial derivative of this thing, right? So we can bring this one to the other side of the equation. So let's do this one first. We have dB dm, just as we had before, but multiplied by the discount factor 1 over 1 plus rho to the power t, right? And that must equal, and now things become more complicated, the dA, right? Because it no longer depends on M, it depends on A. So we first have the dA Then we have how A depends on M, so we have the A, the M. And of course this thing should also be discounted. And the crucial thing here to realize is that this is an instantaneous thing that happens at a particular point in the future, time t. And then what we have is that polluting activity at time t creates trouble at time t for s is 0, right? But it also continues to create trouble at time t plus 1 and at time t plus 2 and at time t plus and so on and so forth, right? So that is why we have a summation here. And our first order condition of optimality is now that this thing here equals this thing here. And things have become more complicated, as you can see. Now we can simplify things. We have a 1 over 1 plus rho to the power t here. We have 1 over 1 plus rho to the power t plus s here. So we can drop 1 over 1 plus rho to the power t, right? That just drops out of the equation because it's on both sides of the equation. And we also know what the A, the M is. Because we have the function for A. The A, the M is simply, well, it's 1 in period 1. If you emit 1 additional ton, then the stock goes up by 1. And then the year after, it goes up by 1 minus delta. And the year after that, it goes up by 1 minus delta squared, 1 minus delta to the power 3, and so on and so forth, right? So that is why I assume this simple specification here, so that we also know this thing. So dropping 1 over 1 plus rho to the power t and replacing the A, the M, with its what it is, 1 over 1 plus delta to the power s. We have this equation here. Because delta is typically small and rho is typically small, this expression here is almost equal to this expression here. So it's beginning to look a little bit friendlier, right? Or a little bit less hostile. Let's now assume that the environment is in a steady state. The slides are on Canvas, so you don't need to take pictures. And the video will be there as well. You're welcome to take pictures. It's just a waste of time. So let's kick the environment into its steady state. Steady state is very simple, right? It means that things don't change. That means that the times subscript doesn't matter. So steady state really means that the atmospheric stock is the same in every period. So AT is A, right? It doesn't change. So then the first order differential equation becomes this. We dropped the subscripts T, which simply means that A is M over delta, right? Okay, I did not actually use this yet. So we have the, well, I'm going to use the steady state. So here we have this thing here inside the summation, but because we dropped the subscripts, this simply becomes this thing here. It's the same everywhere we go, so we can bring it outside of the summation. So then we have a summation over this. As you recall from your calculus, this thing here is equal to 1 over 1 minus this thing, right? This is something that you recall from your calculus. Or you can look it up on Wikipedia. And this thing then simplifies to this expression here. And now I'm going to use that A is M over delta. Going to stick it in here. And what we have is that the marginal benefits of the polluting activity, in this case stock pollutant, is equal to the marginal benefits of the pollution, the marginal damages of the pollution, times a factor. So conceptually, nothing has changed, right? Really what we did here is we said the marginal benefit should equal the marginal costs, but the marginal costs now becomes an annuity, essentially. And this factor is the markup for the fact that this is no longer an instantaneous benefit, but it's a stream of future benefits, right? If indeed everything is in steady state and everything is as nicely linear as I assumed, right? So the damages of pollution are a perpetual annuity. There's one more thing I need to say about this, and that is if you look at the delta and the rho, what matters is the sum total of the two, right? What matters is how fast the pollution degrades in the atmosphere in this case, plus how hard we discount the future. And we can set delta at 0.1 and rho at 0.5, or we could set delta at 0.5 and rho at 0.1. The answer is the same, right? What matters is the sum of the two. So in a way, environmental degradation acts as a discount rate, and this makes intuitive sense, at least to me, that the decay rate acts as a discount rate. The discount rate essentially tells you how fast the value of money evaporates. That you have £100 now, that is, the interest rate is 4% at the moment, that is worth £96 in a year from now, 92, a little bit less in 2 years from now, and so on and so forth. So your money essentially evaporates through the power of discounting, right? Future money is worth less than current money. The decay rate in the atmosphere essentially means not that the value evaporates, but essentially the problem evaporates. Because the sulfur that you put into the atmosphere today will be gone, actually will be long gone in a year from now. If you're talking about CO2, then the CO2 we put in the atmosphere, 1% will be gone next year, 2% will be gone the year after, 3% will be gone the year after that, right? So the damage done by the CO2 also evaporates, because the CO2 you put into the atmosphere in the year 2025 will not all be there still in the year 2026, 2027, and so on and so forth. So the problem evaporates because the pollutant gets assimilated, degraded in the atmosphere. It's turned into other stuff that is not harmful in many cases, right? So conceptually the two are the same, right? One is the discount rate means you care less about the problem, and the decay rate essentially means that the problem becomes smaller in the future, right? And therefore the two are conceptually the same, and actually in the math they show, well, what matters is the sum of the two rather than the individual value of the two. Of course, apart from this thing here, right? Okay, so that's cost-benefit analysis. Now, people do cost-benefit analysis all the time, and people also get very, very cross with cost-benefit analysis and are extremely disappointed with some of its results, and I'll be talking about that after the break. Let's look at one of the key problems in benefit cost analysis or cost benefit analysis. And that is that I put everything on the same vertical axis. And I assume that the benefits at the margin of using electricity can be directly compared to the costs of acidification and climate change and so on and so forth. Air pollution, PM10, PM2.5 caused by burning coal and wood and gas and oil to make electricity, as well as using uranium and stuff. And I just assumed that, well, you can put them on the same graph, right? And essentially what this means is that if this is measured, say, in pounds sterling, then this must also be measured in pounds sterling. Or if this is measured in utility, then this is also measured in utility. Or if this is measured in the number of dying trees from acidification, then this is also measured in the number of dying trees from, or the number of dying trees, right? I assume that you can just add up these things. That is, they are expressed in the same unit. Now, as I said, we're going to spend 3 weeks on how to do this. But as a preview of the conclusion of that, this is difficult, right? And not everybody accepts that it's possible. So if you can't do this, you must do something else, right? And one option that is popular, at least amongst academics, is so-called multi-criteria analysis. And problem with multi-criteria analysis is that there are a great many variants of multi-criteria analysis, but I'm going to take you through a brief preview. It also gets mathematically very hairy very quickly, but we're not going to do that. So there's many variants of multi-criteria analysis. So let's assume that we're in charge of the Ministry of Rural Affairs and Food and Agriculture, DEFRA, and we have to make a choice between the number of badgers that are on this island and the number of cattle that are on this island. And the problem with badgers is that they're wonderful animals, but they carry bovine tuberculosis. And badgers are not harmed by this virus, but cattle are. And the more badgers you have, the more infected cattle you have, and the only solution really is to just kill the herd, right? Because it's so infectious that you can't just isolate the animal that got the disease. No, you have to kill the entire herd, right? So let's assume that there's 3 options. So we have one option with 250,000 badgers on the island, 25 infected herds. The other option is more badgers and fewer infected herds, and then we have fewer badgers again and hardly any cows, right? Now, what would you do in a multi-criteria analysis? So there's 2 things we care about. We care about badgers and we care about cows. Well, option A is just stupid, right? Because we have a lot of sick cows and we don't have that many badgers. So regardless of whether you care more about badgers or whether you care more about cows, option A is always dominated. Nobody in their right mind would choose policy A because it's just stupid, right? So that is easy, right? And this is the important first step in any variant of multi-criteria analysis: exclude the dominated scenarios. And the technical term is dominated. The colloquial term is this. You'd be stupid to do this, right? But options B and C have a clear trade-off, right? Here you have more healthy cows. Here you have more badgers. And you need to choose which of the 2 is more important. So the difference between B and C is 150,000 badgers and 15 infected herds. It's about, if I do it right, if one herd is worth more than 10,000 badgers, right, then C is preferred to B. If one herd of cows, and there's 2,000 cows in a herd, so essentially from this you can derive the break-even point, right? If one cow is worth 50 badgers, then you're indifferent between the two. If you think a cow is worth more than 50 badgers, you would go for this one. If you think that a cow is worth less than 50 badgers, you would go for this one, right? So here you don't answer the question, right? Is B or C better? But you kick it back to the politician you're advising as a policy analyst and say, well, how many badgers go into a cow, right? Value-wise, not volume-wise, right? Value-wise. And if you say, well, a cow is worth 100 badgers to me, then you would go for this option. And if you say a cow is worth only 10 badgers, then you would go for this option, right? So essentially you transform the problem into, you calculate the break-even point, and then you say, on which side of the break-even point do you want to be, right? So that is one variant of multi-criteria analysis. Another variant of multi-criteria analysis, rather than calculating the break-even point and kicking it back to the decision maker or the politician, you let a group of experts vote on the two. And you assume that these experts somehow are benevolent and knowledgeable. Experts, of course, are by definition knowledgeable about their field of expertise, right? Which may not necessarily be badgers and cows. And that is how you decide. And then multi-criteria analysis runs into a problem of acceptance and those sort of things, because who appointed the experts, and are they maybe in the pocket of the farmers, right? We don't know. So there's an issue of legitimacy as soon as you do this, but this is definitely possible. This is a very, very simple case, right? There are more complicated issues. In the week 1, we talked about whether or not you should be vegan. Here we have 5 alternative options for milk. Dairy milk, that comes from cattle. You can also make things that look like and taste like milk from rice, from soy, from oat. Almond milk does not taste like almond, not like milk. It's nice, but it tastes different. So those are your 5 options, right? These are emissions of CO2. Dairy milk is by far the worst. This is how much land you use per certain unit of per liter. Right, this is, of course, this is square meter. It's probably a bit less per liter. No, it's a glass of milk. Really? Okay, you need almost 1.7 square meters of land for a glass of milk, and this is how much water you would use to make so much milk. And this is, of course, not the water that goes into the milk, but the water that goes into the cow, right? So again, you can sort of like see, well, if these are the 3 things we care about, then dairy milk is dominated, right? Regardless of whether you care more about climate or about land use or about water use, dairy milk is always the worst. But if you compare rice to almond, actually you see that the 2 reverse, right? Rice is best, almond is best for CO2, but it's worst for water. And for land, it's a bit harder to see because this one dominates so much. That's because these animals move around and these essentially plants that stand still. The thing is different again. So here it is actually to choose between these 4 options is actually a hard one, right? Because some are better in some dimensions, others are better in other dimensions, and it really depends on how you make these trade-offs. So here, with a simple example, right, where you had 2 options that were non-dominated and 2 criteria that you were looking at, right, it's actually easy to come up with a rule. 1 cow is worth 50 badgers is your break-even. Here you can't really define a break-even. That is simple. It becomes a high-dimensional break-even point. Voting rules then also become very, very complicated very, very rapidly, right? So that is the challenge of multi-criteria analysis, that, yeah, you can sort of like create a picture like this. And obviously, you guys would say, well, price matters, right? Dairy milk is the cheapest. Taste matters, right? Because really these things taste differently. You could say, well, benefits to human health matter, right? The good thing about dairy milk is that it has a lot of calcium in, so that keeps your bones strong, and if you're very young, it helps you grow, and so on and so forth, right? It does not stop at 3 criteria that you care about, and undoubtedly they've come up with different types of milk by now than what you see here. So multi-criteria analysis sort of sounds very exciting and interesting, and perhaps a way out, because we don't have to assume that everything can be expressed in pounds sterling or in utility or in dying trees, but it creates other problems that as soon as you have multiple criteria, as soon as you have very different opinions about what is important, it actually becomes very hairy to say, well, this is better than this, right? You can't really say that. So, this is a good time to break. I'm going to spend about 10 minutes about a couple of other alternatives that are there, and then we're going to look at a few applications of cost-benefit analysis, mostly the super sewer in Anderlonen. Okay, I talked about cost-benefit analysis. I talked about benefit multi-criteria analysis. These are the sort of the 2 options that are preferred by academics. In practice, people use a whole lot of different things, and some of them are listed here. Of course, the list is not exclusive. A lot of environmental policy is set by safe minimum standards, and this really comes out of health, really, and food regulations. And a safe minimum standard works something as follows. You feed a certain substance to a large population of rats, say, or mice, and then you count, if you give them 1 milligram of this, 5% of rats die. If you give them 2 milligrams of this, then 10% of rats die. If you give them half a milligram, then only 1 rat dies out of 1,000, say. And then you have a standard, and you say, well, I don't want more than 0.5% of a population of rats to die if we feed them 1 milligram. So that is safe for rats. And then you say, well, if less than 0.5% of rats die, if you feed them 1 milligram, then a dose of 1 milligram for humans is safe, right? So that is how a safe minimum standard works, literally, right? That is how it works. So there's a couple of arbitrary things here, right? Why is it 0.5% or not 2% or 0.7%, right? So that is a fairly arbitrary thing. And the second arbitrary thing is, of course, that we use rats as a model organism for humans, because obviously you can't ethically do this experiment on humans, right? Rats have a very similar metabolism as we do, so in that sense it's good, but obviously we are much larger and we live in different environments, most of us, than rats do, so it's not a perfect thing. So in a way it is very arbitrary. And in some countries rats are the model animals, in other countries mice are the model animals, and so on and so forth. And you can sort of like see, well, yeah, this is a way of setting a standard, right? But it is arbitrary to a degree. And also it is not a trade-off. And this makes perfect sense if you're deciding on things that where alternative substances that you can use have very similar costs, then it doesn't really matter, there's no real trade-off. It makes sense if there is an acute danger to human health to use a safe minimum standard. But for a lot of problems, there is no cheap alternative to the thing that you are considering banning, and so on and so forth. Or there is no obvious model organism, right? I mean, if we're talking about whether or not we should allow certain pesticide residues to be in the hamburger that you eat, then it makes sense to do this. But if we are deciding about environmental questions, like how much sulfur we should have in the atmosphere or how much CO2 we should have in the atmosphere, there is no obvious, because it's not just a problem for human health and it's not just people ending up in hospital or worse. Well, there's all sorts of environmental consequences, there are all sorts of economic consequences apart from health. Then it is actually very difficult to define a model organism to do this. So yeah, it's often used, but very limited and to a degree arbitrary. Another thing that people are very keen on now is to say, well, we're going to organize a citizen jury. And France in particular is doing this at the moment more than any other country. And essentially what you do there is you have a complicated environmental problem, a decision needs to be made. What you do is you gather 200 people randomly selected from the population, and you put them in a room together with experts for 2 months, and you let them listen to the evidence from all sides so that they're informed, and you let them debate for a couple of weeks about what is the best course of action, and then they vote, and that is how you set your policy. You may think, well, this is appealing. Of course, there's all sorts of manipulation going on, like who was selecting the jury, who is selecting the experts, what are they listening to, and in a way it is really, this is the job of parliament, right? Politicians have been elected to make decisions like this, and they should be doing it. But it's a way for politicians to sort of like cop out of their responsibilities, to essentially create a special parliament for a particular decision. You can also just kick it to the general population, and most of you are from the UK. Organizing referendums can be very dangerous because they can be hijacked. People do not necessarily understand their own interest and may make very similar or very silly decisions. Another popular thing in policy circles is to say, well, we have an environmental problem, we're going to solve it. And the way we're solving it, well, we don't know really what are the costs and what are the benefits. Let's just use the best available technology. The one that is the least polluting, and we're going to say, well, any other technology is forbidden. Again, that sounds attractive. You're solving the problem. But you're not, you're using the best available technology. You're not pursuing some sort of pipe dream of eliminating all pollution, right? No, you say we're just going to use the best available technology. The problem with saying this to an engineer is we're going to use the best available technology. What engineers do is they create new technologies, right? That is what they do. So if you say we're going to use the best available technology, then you create sort of like this incentive to put new technologies on the market that are better, but perhaps also more profitable. So this is often amended with best available technology not exceeding excessive costs, and then it becomes arbitrary again, right? Because you're no longer minimizing pollution, but you're also sort of like weighing it against the cost. So it becomes arbitrary or cost-benefit analysis sort of through the back door. Precautionary principle is very popular as well amongst politicians. There's two variants of the precautionary principle. One is that uncertainty is no excuse. The fact that you do not fully understand the consequences of your action is no reason to be inactive. And you used to see this a lot in the more conservative circles in the United States, where they say, oh, well, we don't really know what climate change is going to do to us, so perhaps we should just wait and sit back until we know the consequences of climate change in more detail. That is a silly way to make decisions. There's very few walks in life where we wait for all uncertainty to be resolved before we make a decision, right? If you decide you're going to study economics, you do so before you know the consequences of that choice, right? You make that investment anyway. If you decide to get married or buy a car, you do not know the full consequences of that decision. You think you make the right choice, and it's a long-term investment in many ways, but you don't know the full consequences of this particular decision you make. So why would you make the decision anyway, right? Similarly, for environmental protection, you can never know the full consequences of your action, right? So this is never a reason not to act. So that is one interpretation of the precautionary principle. The other interpretation of the precautionary principle is that it's better to be safe than sorry. That is, if there's a new pesticide and we don't know the consequences of using this pesticide, we don't know how many bees it will kill and so on and so forth, then we better not use this pesticide, right? And this is the European interpretation of the precautionary principle. And the European Commission and the UK government as well does not allow a lot of chemicals to come on the market because the consequences of using these chemicals is unclear. And again, you may say, well, this is a reasonable way of making decisions. There's two problems with this version of the precautionary principle. One is you don't know the opportunity cost. And the precautionary principle has been used to block a whole load of new pesticides in agriculture. Yes, it is true that the full consequences of these new pesticides are not known, but the opportunity cost of not allowing in new pesticides is that old pesticides will continue to be used. And those old pesticides we do know the consequences of, and they can actually be pretty bad. And in many cases, the old pesticides are much worse than the new pesticides that are being blocked on the basis of the precautionary principle, right? So this is not necessarily the right thing to do. The other thing that you have with the precautionary principle is that you just look at the environmental harm. You don't look at what sort of benefits would this new chemical bring, right? So it's a very one-sided type of analysis. It makes perfect sense if the costs are low, the environmental or the economic benefits are low, the environmental damages are high, then it makes sense to do a one-sided analysis and only look at the environmental side of the equation. But if the two are more finely balanced, then this will lead to pretty desperate recommendations. The most popular, the most used way of setting standards in the environment is essentially arbitrary. Or at least it's arbitrary from an environmental perspective, it's arbitrary from an economic perspective. Most standards that are set can be understood in terms of power play between politicians. You can interpret it as ways of satisfying certain constituents or certain lobbyists. But it doesn't make much economic or even environmental sense, right? So this is how most environmental policy is set, sorry to be cynical. Final thing I'm going to say, and we're going to come back to this in week 7, is to use cost effectiveness analysis instead. So cost benefit analysis is essentially efficiency. You're trying to maximize total welfare. Cost effectiveness analysis is a subset of this. Essentially what you have in cost effectiveness analysis is that you've set a target and then you wonder, how do I meet this environmental target, this emissions target, at the lowest possible cost? And that is a useful thing to do, but of course it does not tell you anything about whether the target was set at the right level, right? It just tells you how to best meet your goals. So this is the sort of stuff that is going on as an alternative to cost-benefit analysis, which not perfect, maybe the superior way of doing things. Half an hour left. So I'm going to talk about two more things. One is the application of cost-benefit analysis. I'm going to start with sort of general principles, but instead of talking about that at length in an abstract sense of the word, I'm going to look at the London super sewer just to show how it works in reality. So applied cost-benefit analysis goes back to Cretilla, who you see here, died a few years ago, who essentially set this up as a tool. And essentially what Cretilla did was he took the tools that were used in mostly companies for project evaluation, for the decision whether or not to invest in a new plant, or whether or not to buy a company or to expand into a market, set up a new export market or something like that, or start a new product line. Those tools of project evaluation, Cretilla said, well, we can also use this for public decisions, and we can expand those tools. And of course, a company only looks at its own bottom line, right? Its private costs and its private benefits. We can expand this tool to also look at social costs and benefits. Sounds trivial in retrospect, but he was the first to suggest doing this, and also the first to actually start doing this. And this requires systematic counting and valuation of all relevant costs and benefits to society as a whole. And it's a strictly utilitarian and humanist way. So benefits are anything that increases human welfare, and costs are anything that decreases human welfare. And then what you do, and there's two versions of this, if you have a single project, then you choose to do this project if the benefit exceeds the cost, or if the benefit cost ratio is greater than 1. And you don't do it if the benefit cost ratio is smaller than 1. If you have a number of projects and a finite budget, then you first fund the project with the highest benefit cost ratio, then the one with the second highest benefit cost ratio until your budget is exhausted, right? Or if you have sort of a continuous choice, say the tax that you want to apply to sulfur emissions, for instance, then you want to, in continuous space, want to maximize the net benefits minus cost, much as I did before the break. So that really is what Krutila suggested, and as I said, it's almost trivial in retrospect, but he was the first to say, look, we can take these corporate tools and bring them to public policy. Cost-benefit analysis has been used for all sorts of stuff, for environmental policy as a whole, for looking at specific projects, for environmental management. Here are just a number of examples where cost-benefit analysis has been used. This is, I forget which dam this is, Thames Water I'm going to talk about. It's been cost-benefit analysis of the London 2012 Olympics. There's been plenty of cost-benefit analysis of the use of fossil fuels and the environmental damage that comes with it, and as well as the economic benefits that come with the use of fossil fuels, has been applied to pesticides and what it does to particularly bees. It also been applied to the HS2, the high-speed train from London to somewhere up north, but it's a bit unclear how far and how fast and when. These are all ex ante cost-benefit analyses, but of course you can also apply it ex post to look at past environmental policies. There's a couple of people who have been fairly active in this. David Pearce is one example, who's looked at a whole range of environmental policies from the EU and said, that doesn't pass the smell test. The champion of this is Bob Hahn, who has done this. Bob, I don't know how old Bob is, but he's old. He's been doing this forever, particularly looking at the US individual regulations. And one study he did now 30 years ago, he's still going, by the way, he's still doing this sort of stuff, found that only 50% of regulations by the federal government in the United States have greater benefits than they have cost, right? And in other words, 50% were not worth the money. So there's all sorts of activity going on, ex ante as well as ex post. The question then is, of course, can we get this right? Cost-benefit analysis may be systematically biased, sometimes pro-environment, sometimes anti-environment. And the big question here is, what do you count? And how do you count it, right? And economic costs are typically very well defined, and there's powerful people who start making noise if you impose too much cost, too much of a burden on them. Whereas for the environment, not necessarily powerful people speak up, right? And that would sort of like lead to a political imbalance and a systematic bias, and that's what Gray found. Systematic bias against pro-environmental stuff. And the other issue is, of course, and we talked about this at length in week 1, is that this is a very utilitarian way of looking at things, and there may be other things that are just as important, if not more important. As soon as you're saying we're maximizing the net present benefit, you're essentially saying we're maximizing human welfare, right? The two are essentially the same. And there may be other things that are more important. One thing that is very difficult in this is the distribution of the benefits and the costs. What I just did in the example before the break is that I just assumed there were benefits and assumed there were costs, and I did not talk at all about who reaps the benefits, And who bears the costs? I just assumed that there was a cost function and a benefit function. This is first and second welfare theorem, right? So essentially, the benefit cost analysis is very much in the first welfare theorem. We're trying to maximize utility, trying to maximize welfare. And then the question is, yeah, but if total welfare goes up, is this a real Pareto improvement, or are some people really hurt? And then, of course, you could say, well, Calder-Hicks, right? Total welfare has gone up, so the winners could compensate the losers. And then it is a Pareto improvement. But of course, the fact that the winners can compensate the losers does not mean that they do compensate the losers, right? So that is something to keep in mind. If you have a strong government that is committed to these sort of things, then compensation can be made through taxes and through benefits. But the fact that it can be made does not mean that it will be made, right? I recall doing a bit of policy advice for the Irish government. It was about the introduction of a carbon tax. And we did all the calculations. We did not just do the cost-benefit analysis for the sum total of Irish society, but we also did a cost-benefit analysis for individual members of Irish society. And we found that if you apply a carbon tax, then the poor are going to hurt, right? Because energy is a necessary good, and they are going to be hurt disproportionately, or the inflation that is induced by a carbon tax is going to disproportionately hurt the poor. But we also said, well, if you actually reserve 30% of the revenue of the tax for an increase in tax credits and for an increase in benefits, increase in the tax credits and increase in benefits disproportionately benefits the poor, and you only needed 30% of the carbon tax revenue to offset the pain for the poorest in society, then it is actually becomes something like a real Pareto improvement. So we did all those calculations. We had buy-in from the minister, who was a member of the Labour Party, that this is what she was going to do, right? So we came up with a policy proposal that was an actual Pareto improvement. They got the carbon tax through Parliament, and then she reneged on a promise to compensate the losers, right? Even though she was Labour and even though she had made very sincere promises before. So the fact that compensation can be made does not mean that compensation will be paid, right? Some people sort of say, well, these equity issues, yeah, you can look at it for every individual project, but really a government is doing a million things, and if the benefits and the costs are sort of like randomly distributed across the population, and if you do a million projects at the same time, then the benefits and the costs will sort of wash out, and the losers from one policy intervention will be the winners of another policy intervention, and it all washes out in the end. That's an interesting argument to make. In week 10, we're going to argue that no, these things are systematically correlated and they do not wash out. But we need to park that until almost the end, right? These are important things. So 20 minutes left. What do you need to do in a CBA? And then I'm going to look at the super sewer, and we're going to actually do these things. You start always with saying, well, something must happen because, right? You start with a rationale for intervention. And then the second thing that you do is you say, well, these are the options that are on the table. These are the things that we could do. And of course, you also always need to include the counterfactual or the baseline. What if you don't do anything, right? Because that is then measure what we measure everything against. Then you need to decide standing and say, well, these are the things we're going to look at. These are the people that count. These are the animals that count, right? Then you need to identify all the possible consequences of both inaction and the list of options that you have identified. Economic, ecological, and so on and so forth. Once you have identified all the things that matter, you need to somehow make a prediction. If you're going to do nothing, this will happen. If you're going to do A, something else will happen. If you're going to do B, something else will happen again, right? And you need to predict this over this lifetime of the project. Then you need to add up everything, but you cannot add badgers to cows, right? It doesn't make any sense, so you need to find the equivalence between badgers and cows so that you have animals, right? And you need to compare that to the costs of your project as well, so you want to put a dollar value or a pound value on this. Discount everything to the present day, add it all up. By now you have made 1 million assumptions, right? So you need to do a sensitivity analysis. If I change this assumption by a little bit, will my conclusions fall over or will they stay the same? How robust are the results to reasonable changes in the assumptions that I made? And then once you have done all that, you can sort of say, well, option C is the best, right? So that is what you need to do. And this all sounds abstract, so let's look at the London super sewer. And there's a whole bunch of things going on in the UK public sphere. There's been a debate about the third runway of Heathrow since 1947. Really? 1947 was the first time somebody suggested that Heathrow needed a third runway, and we're still talking about it, right? Very publicly. Similarly, HS2 is another sort of big project that we just keep talking about and keep changing and doing. The London super sewer is not one of those. This is much lower down the public attention, which is good because this is actually was built rather than discussed and discussed again and discussed again and some more. This one is actually built, it's almost done. The problem with London and its sewerage is that most of the sewer system in London was built during Victorian times, and it's breaking down because it is very, very old. It was obviously built with technology of the time and for a city that was much smaller than today's London, right? So London's sewer system is a mess, right? Is I think the best way to describe it. The alternative that they thought up was to build a new sewer. And they called it the super sewer. And it is fairly expensive, billions of pounds. And the first step, as I said, is the rationale, do we actually need to do something? And the answer is yes. It's not just that the sewer system is completely out of date. One problem, and this is not just in London, is that sewer systems carry human waste, right? That's what they're there for. But across the UK, they also discharge rainwater. And that is not something that I should tell you guys. This is not news to you. If there is heavy rain, then the sewer overflows And if the sewer overflows, then it takes all the shit out into the street or into the river, right? And this is an issue. This is a big issue, and a lot of people have talked about it in recent years in the UK, and that is, or in England and Wales, I should say. This is because we actually changed the monitoring system of the sewer system. It used to be that these things happened, but nobody knew, or the people in the system knew, but the general public was unaware. And since the previous government introduced this new monitoring system, people have become aware that these things just keep on dumping raw sewage into rivers, onto beaches, and so on and so forth. So this is now generally known. My wife works in sewage. She's an engineer, making sure that these things don't happen. The insiders knew about this problem, have known about this problem for decades. So this is a problem also in London, also around the Thames. The issue is visual appearance, right? The Thames turns brown. Enormous amount of fish get killed because it's toxic, or because algae grow much faster and take away all the oxygen. This is a, I don't know where this is, somewhere along the Thames. These are just shore full of dead fish, right? It also creates health risks. Really, you don't want to swim in sewage. This is David Williams, who you know, who is stupid enough to go swim in the Thames. Stuck his thumbs up, I'm so funny. No, you're not, David. Got very, very ill because it's hard to swim without ingesting water, right? So, yes, something needed to be done. The proposal, something as follows. Essentially, like, we're going to build a big tunnel. So this is the North Sea. Here we are all the way in Hounslow, right? So this is Richmond. So this is fairly big, right? They're going to build. They have built an enormous tunnel to carry all the sewage. From here it's carried to Beckton to be treated. From here it's actually carried towards Hammersmith to be treated and stored there. Of course, then you also need all sorts of subsidiary pipes, and you need all sorts of pumping stations there. So this is a big project, right? This is not something that you just do in an afternoon. The tunnel that they built is big. This is an actual picture, not some projections. And yeah, you can, for most of the tunnel, you can drive a truck through, right? That is how big it is, and it's all under the Thames. So that is what they did in the end. At the beginning, of course, they needed to look at various options. New treatment plants, expanded treatment plants, storage, transfer, and so on and so forth. There's all sorts of options you can do, all sorts of technical configurations, and you could put such a system. And in the end, they identified 24 alternative solutions, right? Then if you don't do any of the 24, what would happen? Nothing, or would maintain the status quo. Essentially what they used to do, still do to a certain extent, is to essentially send boats onto the Thames to scoop up the shit, right? That is how the problem used to be solved. And as a result, people were dying, and fish, well, people got ill, fish were dying, right? Who to include? Who has standing, right? And this was an issue, a big issue. They actually went through 2 rounds. In the first round, they sort of said, the people of London count. But actually, at the moment, they're dumping a lot of shit into Surrey, and the benefits of not doing that anymore to the people who live in Surrey were originally not counted, right? That's a bit of a peculiar decision. It's a London super sewer, but London is actually exporting its sewage, right? So perhaps you should count these people as well, right? Who pays for this? Essentially, the decision was made that this will not be paid for through general taxation, but this will be paid for by everybody who's a customer of Thames Water, which is actually a bit of a wider catchment area in some ways, smaller in other sense. It's 5 million households in London and the southeast, and it will be paid for through water bills, which is again a decision that you made. You could have done it through general taxation. What do you include? What do you exclude? At the end, these were the costs that were included, and again, the projector is pretty bad. Capital expenditure, operating expenditure were included. What was not included on the cost side are the disruption of construction, the noise during construction, the dust generated by construction. What was not calculated was the energy used during construction. They said, well, that is all zero, right? Essentially, when you say, well, this does not matter or this is not included, you essentially assume it to be zero, right? Or you assume its value to be zero. And by saying we're going to look at the costs, but not at the CO2 that comes out of the construction, you're essentially saying, I don't care about CO2. That is essentially what you're saying. On the benefit side, they looked at visual amenity, they looked at health risks, and they looked at fiscals, and that was it. The avoided cost of the bobbler and skimmer boats was not included. A lot of stuff were not there, right? Cultural heritage, I mentioned this one, cultural heritage wasn't there. Ecological impact, they only looked at dead fish. Fish are the only animals that matter, right? Other plants and stuff do not matter. But you have to do so, right? Because they had these 24 projects, 24 alternatives, and of course the baseline not doing any of the 24. Project that spans over decades, so you really need to be careful in what you do, otherwise the work just keeps multiplying and multiplying and multiplying, right? So 50 years, 24 projects, 4 dimensions is what they decided to do. All the rest was excluded. There is such a thing as optimism bias in whenever you do a project, and it's been recognized by the government, and this is actually comes out of a government document. Optimism bias said that for standard buildings, essentially the capital expenditure is somewhere between 2 and 24% higher than initially promised, right? Typically, if it's a standard building, then people overrun by 1%, perhaps by 4%. But if you're looking at non-standard civil engineering, and the super sewer definitely is non-standard, then typically, or capital expenditure is somewhere between 6 and 66% higher than initially promised. So this is something that you need to take into account. Capital or equipment sometimes can be 3 times as expensive as initially promised. And things typically take much longer than your engineers have promised, right? From sometimes it's 1% longer, sometimes it's 25% longer. So those things need to be taken into account. These projections are projections, right? Then they needed to monetize everything, because everything needed to be comparable to the capital and operations expenditure. And these are the numbers that they used. So health risks, whenever there's sewage in the Thames, that is going to cost 38 pence per person per day. Fish kills are worth 151 per event. Sewage litter, if that's visible, is worth 182. These are the right numbers? God knows. They occur over a 50-year period, so you need to discount everything to today. Don't need to tell you guys that the discount rate is fairly important. If we invest £100 today and we get an interest rate of 2.1%, then that is £800 in 100 years' time. If the interest rate is 10%, then it's worth £1.4 million in 100 years' time. So this is the value of compound interest, right? Vice versa, 1.4 million in 100 years from now is worth £100 if you use an interest rate of 10%, and it's that 1.4 million in 100 years' time is worth the same as £800 in 100 years' time if you use an interest rate of 2.1%, right? So discounting is extremely important. The project that they eventually selected, the one that I showed the diagram of, had a net present benefit of somewhere between 3 and 5 billion. So they did the sensitivity analysis as well and said, yeah, this is worth more than it costs. All sorts of things that can go wrong here, right? We're essentially talking about things that aren't there. We're talking about hypothetical projects in a future, right? So it is a matter of forecasting. And that means that all sorts of things can go wrong. I talked about exclusion, I talked about measurement errors, talked about forecast errors very briefly, talked about valuation. These two things I haven't really talked about. Sometimes we see that, and I think this is formulated by George, I think this is formulated incorrectly. What politicians or decision makers tend to do is not so much hire mercenaries or guns for hire. They're not so much hiring people that do as they are told, but typically you hire those experts that you know are of a certain ideological inclination and that agree with you. So Tory ministers would hire right-leaning economists, Labour ministers would hire left-leaning economists. And it's not so much that these people do as they're told, but they're selected to give a certain message because you know from somebody's past what sort of things they will come up with, right? And that's definitely an issue here. But there is sometimes real pressure from the ministry, who is, after all, I mean, most of this is done not by independent academics, but it's done by hired consultants, right? And that means that, yeah, they control whether you get paid in the end or not, or whether you get a new contract in the end. So people are subject to pressure, and sometimes cost-benefit analysis is just done to justify decisions that have already been made. Talked about all these things already. So go back to the super sewer. It actually, so they put it to a proposal. They said, oh, this is going to cost too much. Then they did it again 4 years later and then actually said, yeah, this is a good idea. It's mostly because they included Surrey in there, as I said. They are actually almost done. This slide is a little bit older. So construction is not started, construction is almost finished, and really the main bits are there already. You don't believe me, you can go to this particular site and look at all the things that are going on. They're almost done. So just to wrap up, all sorts of advantages to cost-benefit analysis. It's transparent, accountable, consistent, it promotes rationality and efficiency, and it increases the pie. All sorts of disadvantages as well. It is very complex. If you really want to do it on a complicated project, it is very complex. And that means that there's all sorts of things that can be massaged in one way or manipulated in another way. Or sometimes the problem is just too imprecise and too big to be useful. But definitely is a way of thinking through a problem. I think it offers certain advantages. As always, don't take it for granted, don't take it as gospel, but work with it and see what it says. That's all for today.